this video, Columbia University's doctoral candidate, Rashidul Berry, will teach Newton.
In this lesson, we will try to understand the difference between normal force and weight. When you apply push or pull on a box, it changes normal force, but it doesn't affect the weight. So for example, there is a 10 kilogram mass sitting on a table. If someone, so what is the weight of this box? The weight of this box is 98 Newton. 10 kilogram times 9.8 meter per second square, which is 98 Newton. Now if someone push it, the normal force, the table has to apply more upward force to keep it balance. What if someone apply upward force? Then there would be less normal force, because the table immediately would realize that there is someone pulling the box. So now in this problem, we're going to try to understand how the normal force changes if you change the pulling force or pushing force. So let's get it started. Right, so first we're going to do, let's do push. So a push. So I have a object, the same object over here. So I have the object, and that is 10 kilogram sitting on this table. So what is the weight of this object? The weight of this object, remember, the force is equal to weight. We can write it a little differently. Force is equal to Fg, which is equal to Ma, which is equal to Mg, which is equal to the weight. All right. So why is because the reason is very simple, because SI unit for force is Newton, SI unit for Fg is Newton, SI unit for Ma is Newton, SI unit for Mg is Newton, and SI unit for weight is also Newton. So let's try to find the weight. So what is the weight of this box? So we're going to use the simple equation. Weight is mg, m is 10 kilogram, and g is 9.8 meter per second square. So weight is 98 Newton. So 98 Newton. So weight of this box is, the box is 10 kilogram, weight of this box is 98 Newton. So this force due to gravity, and the table apply a force which is equal in magnitude, opposite in direction, making the net force 0. So the acceleration is also 0. So what else is also 0? Velocity is also 0, because the object is at rest. So Newton's first law. All right, now let's change the pushing force now. All right, so let's see 0, and then how that changes the weight and how that changes the Fn. With 0 pushing force, the weight is 98 Newton, and the normal force is also 98 Newton. Now let's say 10 Newton, and then 50 Newton. All right, so if we apply 10 Newton, how that would change? So let's see. All right, so let's put the table over here. Okay, so this is the table. Make the table small so I have more room. So what would the weight be now? Weight is still 98 Newton. so weight doesn't change, so weight is still 98 Newton. So the normal force, now let's see how many force acting on it. Pushing force is 10 Newton, so pushing force is 10 Newton, and the normal force is, we're gonna have to find normal force. We see that the normal force is 10 plus 98, so it's gonna be 108. So normal force is 108, but we can definitely prove it. We can definitely show why the normal force is gonna be we can show why the normal force is gonna be 108. So Fy, we write Fy, all the forces acting at Fy is equal to F push, Fn, and Fg. So let's write the positive one, Fn minus F push minus Fg. So at the y direction, what is the net force? Net force is 0. Why net force is 0? Because if F push is less than the weight, then the net force is 0. Keep that in mind. So 0 is equal to Fn minus Fp minus Fg. So Fp plus Fg is equal to Fn. So Fp is 10 Newton plus 98 Newton is equal to Fn. So Fn is equal to 108 Newton. So which one is the longest, which one is the largest vector? Fn is the largest vector, so we have to change it. So Fn is the largest vector, so this is Fn. Which one is the second largest? 98 is the second largest, so we're going to change 98. So 98 is the second largest. 98, we're going to write 98 with this, so 98, so this is 98 Newton. What is the smallest? This one is the smallest, so we're going to also make it red. Alright, so two vector acting downward and one vector acting upward, and if you add them both, let's put the red one, F push and Fg, which is equal in magnitude with Fn and opposite in direction, making net force 0 at the y direction, acceleration is 0 at the y direction, velocity is 0 at the y direction. So Newton's first law. Okay, so problem scenario number 1, Newton's first law. Scenario number 2, Newton's first law. So we're gonna update this table, 108 Newton. This is what we said before, that the normal force changes but the weight remain the same. We're gonna do it 50 and then we're gonna move on to pole. So let's do it 50. Let's put the box on the table. 10 kilogram box is still, as you see, that the weight. All right, so now the weight is still 98 Newton. Normal force and pushing force we see 50 Newton. So normal force has to be pushing force is 90 Newton, so normal force has to be 148. So this is normal force is 148. Now we have to fix the vector. How do I know normal force is 48? So the 50 plus 98, I can show you the math. Fy is equal to Fp minus F push minus Fg. Fy is still 0 because F push is less than Fg. So 0 is equal to Fp is what, Fn is what we try to find, minus Fp is 50 minus 98. So Fn is 148 Newton. So if that is the case, 140 Newton, then we have to fix something, and that is the vectors. So this is supposed to be the longest vector, just like the other scenario, so I'm going to make it longer. Yeah. Okay. So try not to edit now, okay? try to take 2-minute break. Alright, the second longest is FG, so I'm going to make the second longest one. Of course, I'm going to make it different color, so it's going to be all the downward arrow. I'm going to make it different color. Let's make it red because I want to be consistent with the one that I did before. So FG. Alright, so I have one more, and that is the app push. App push is 50, so app push is 50. 50. So that app push. So now I see that I have two downward, the red, one red and two red, two downward, and I have one upward, and I think they are equal in magnitude, opposite in direction, making the net force 0, making the acceleration is 0, and making the velocity is 0. However, it changes the normal force 148, and as you see that if you apply 50 push, if you push the box by 50 Newton, then the weight is still same. However, the towel has to do so much to keep the box still at rest, and towel has to do so much, and that is 148 Newton. As you see that the more you push, if you apply 0 Newton, if you push by 0 Newton, the towel has to exert 98 Newton in order to keep the box at rest. If you push by 10 Newton, the towel has to do so much. But if you apply 50 Newton, towel really have to do so much. Now let's see what happens when you apply, when you pull instead of push. So app pull, let's say this is FG and this is FN. So we start with 0 and then 50 and then 100. So we have three extreme case: small, medium and large. And let's start from here. So this is our towel, and let's put the box on the towel. Why not? Let's box on the towel, and box is 10 kilograms. So now the weight is, as I said many times, by now you know how to find the weight. Weight is 98 Newton. Okay, and normal force would be equal in magnitude but opposite in direction, is because the towel wants to keep the box at rest, so they cancel each other, making the net force 0, making the acceleration is 0, and making the velocity is 0. So this is the case, Newton's first law. Alright, so now we're gonna change the scenario, and let's see what happened when you change the scenario. So the box of here is a 10 Newton box, 10 kilogram box. So the FG is the same, is still 98 Newton. However, F pole is 50 Newton. This is F pole, and the normal force is what? So now you see that the towel knows that someone pulling it, so towel become, towel is a smart thing. Towel knows that someone pulling, so towel doesn't have to do so much. So towel doing only 98 minus 50, and that is 48. So towel exert only 48 Newton in order to keep the box at rest. How did I do that? I write Fy, all the forces acting in the y direction, including Fn, Fp, and Fg. Fp is positive, Fn is positive, they are pulling force, and Fg is negative because they are downward. Fy is 0, once again, is because F pole is still smaller than Fg. So 0 is equal to Fn plus the Fp is 50 Newton minus 98 Newton. Alright, so Fn actually is 48 Newton. Alright, so if Fn is 48 Newton, then there is a problem we have. I see our vectors are not drawn correctly, so I'm going to make sure that our vectors are drawn correctly. What is the largest vector is the gravity, acceleration due to, the force, the gravitational force or weight, which is 98. So I'm going to make it bigger. Of course, I'm going to make it bigger. So this is the weight. The second biggest is for the pulling force. So I'm going to make the pulling force second biggest. So this is the second biggest. What is the smallest? The smallest is the normal force. Now table is happy in this situation is because table does not have to exert that much force. So do you think that 2 upward arrow is equal to the 1 downward arrow? I bet. So that creates normal force 0, net force 0, acceleration 0, and velocity 0 at the y direction. So this is the case of Newton's first law. Now we're going to make it extreme. What do I mean? I mean what I said. So now we're going to put the box on the table, and this time we're going to apply 100 Newton. So if we apply 100 Newton pulling force on the box, what happened? What would be the normal force? What would the normal force be? This is a good question, but let's first find the weight. But before that, let's update the table. When pulling force is 0, weight is 98, normal force is 98. When pulling force is 50, weight is 98, but normal force is 48. When pulling force is 100, weight is 98, and normal force is normal force is 0. You know that because the table is off the ground. Why the table is off the box is off the table is because there is a net force. How much net force acting on the box? Let's see. 100 minus 98, and that is 2 Newton. Can we show it by Newton's second law? In Newton law, yes. Fy is equal to Fp or Fn minus Fp minus Fg. Fn is 0. Why Fn is 0 is because there is a net force we see at the y direction. So Fy, so since there is a net force at the y direction, we're going to use Newton's second law, which is ma. Fp is 100, so negative 100, and Fg is 98. So this is positive 100 because the pulling force is always positive. This is positive, okay, minus 98. So ma is 2 Newton. Okay, so the mass is 10 kilogram. So acceleration is 2 Newton over 10 kilogram. So then acceleration is 0.2 meter per second square. Okay, so what do we see? We see that this is Newton's second law, example of Newton's second law. So this is everything we did so far together. Few problem we did it. Few problem we pushed the box and we saw that it does not affect the weight of the box. However, it does affect the normal force. In case the table has to exert more forces to keep the box at rest if you push it. So table probably doesn't like it. On the other hand, when you pull the box up by exerting upward force, also it doesn't affect the weight, but still it does affect the normal force. In a way that table kind of likes it, because the table, the more forces you apply at the upward direction, the less forces table have to apply on the box, so that box at rest. Thank you.